In this video, we're going to talk about one of the business applications that involve using binary variables, the capital budgeting problem. In capital budgeting problem, the question is which project or which activity to undertake, to invest in, right? So we have a list of activities or projects, and we want to pick the best set of activities or investment project that lead to the maximum profit at the end of the day, or maximum net present value in this case, right? This is pretty similar to the portfolio optimization problem that we solved before in chapter 11, except that there we had the decision that we wanted to make was how much money to invest in each alternative. The difference here is that in capital budgeting problem, we usually know exactly how much capital or how much cost we need to incur for each project. So the amount of the dollar amount of each project is pretty much fixed. You have a very good estimate of that. The decision that you have to make here is whether or not you pick the project, whether or not you undertake the project. All right, so it's different. Here we're dealing with binary variables. And the example that we're gonna solve here is actually a pure binary integer linear programming type of problem, right? And we wanna maximize the net present value. So the specific example that we are going to solve here, the ice cold refrigerator company, they're actually looking over the next 4 years. So the planning horizon is 4 years. And they have a limited capital. They have a limited available capital per year for the next 4 years. And they have a list of 4 projects, 4 activities that they can pick from. And they want to maximize the net present value. So here is the list of projects. So they have 4 projects, and they know exactly how much it's going to cost for each project, how much capital they need in each year for each project. They know exactly how much the present value or the net present value is going to be at the current time, the equivalent of basically returns and costs or revenues and costs at the current time is going to be, let's say, 90,000 for plant expansion. So, and then they know exactly how much money, how much capital they have available at each year. So let's say at year 1, they have $40,000 available to invest. They're expecting to have $50,000 available at year 2 and so on. So like I said, there are 4 projects: plant expansion, warehouse expansion, new machinery, new product research, all right? So now we want to find the best set of projects. Out of these 4 projects, we want to see which one they can afford that leads to the maximum present value, the maximum sum of present value or net present value, all right? So decisions here is, let's say we have 4 projects. The decision is whether or not to pick each one of these projects. So 4 projects, 4 decision variables. And then the decision variables are binary, 0 or 1. 1 meaning, yes, invest in the project. So plant expansion, we're going to define 1 decision variable for this one, whether or not to invest in plant expansion. So if we denote that by P equals 1, if the plant expansion project is accepted, meaning that we invest in that project. 0 means no, we reject, we don't invest in this project. W for warehouse expansion, M for new machinery, R for new product research, all right? And we define all of these 4 decision variables as binary decision variables. So now the problem has 4 constraints. We were looking at 4 years. We're looking at, we have a limited amount of money, limited amount of capital at each year. So we want to make sure that we don't go beyond our capital availability. All right. So we want to maximize the net present value, the sum of present value of projects if we take them. So you multiply, let's say 90 by P. So 90, let me go back to the table here. 90,000 was the present value of plant expansion. So you get this. This is going to realize if you invest in plant expansion. So when you multiply 90,000 by P, so P can be either 0 or 1, right? So if P is 0, so this is going to go away. So you don't get any present value out of that. If you invest in plant expansion, P is going to be 1. So 90 times 1, 90 is going to be realized in present value, and so on. So 40 times W plus 10 times M plus 37 times R. So that's the present value that you want to maximize. Now, what are the capital constraints? This is a very simple example. We just look at the capital constraints per year, and that's the only set of constraints that we're looking at. So for first year, the capital that we use should be less than or equal to the maximum capital that we have available. I'm just going to discuss the first one, and then we go to the Excel and try to solve this. So for the first year, the amount of capital that we need, let me go back again to my table here. In the year 1, I'm going to need 15,000 if I invest in plant expansion. So by multiplying 15,000 by P, 15,000 times P is going to be my capital requirement for plant expansion. Now, if plant expansion, if P is equal to 0, meaning that I'm not investing in that, in plant expansion, 15,000 times 0 is going to be 0. So I don't need any capital I don't have any capital requirement for this project at year 0. But if P is equal to 1, 15,000 times 1, 15,000 is going to realize I need this money if I invest in this one. 15,000 times P plus 10,000 times W plus 10,000 times M plus 15,000 times R should be less than or equal. So this is the total amount that I need, that I require if I plan to go with this investment plan. That has to be less than or equal to 40,000. I can't violate this. I can't exceed this value, right? So this is the total amount that I have available. I have to respect this. So if I write it down, this is going to be my constraint for year 1. And if I continue, I will have 4 constraints. One note here, you see in the table, all the numbers are in thousands. And in my formulation, I have removed all these thousand. So that is absolutely fine, because if you multiply or actually divide the numbers, all the numbers, all the parameters, all the right-hand sides, left-hand sides, and all the coefficient in the objective function, it's not going to change anything. Actually, if you multiply these numbers by any constant number in the objective function coefficient, if you divide them by anything, if you add any constant number here, it's not going to change your optimal solution. All right. For the constraint, as long as you multiply or divide them by the same value, both right-hand sides and the left-hand side, it's not going to change anything, right? So even if, let's say for one of the constraints, I multiply all these numbers at both sides by 1 million, all the parameters at the left-hand side and the right-hand side, all the coefficients by, let's say, 1,000, 1 million, Or if I divide them by 1 million, it's not going to change anything. It's not going to affect my solution. All right. So that's just for writing less number of zeros. I just factored 1,000 here. So if I go now to my Excel and just review what I've done so far, my formulation, and try to start solving it. So this is the set of parameters that I had in the question. And this is the formulation that we just saw it, right? This is the formulation. Now, let's go ahead and create our spreadsheet model and try to solve it. So the decision variables, I said we have four projects, 4 activities in capital budgeting type of problems, where the decision is only whether or not decision variables, and it's going to be only about invest or not. So I'm just going to highlight these 4 cells, and then the decision variable, invest or not. So that's the decision that I'm trying to make. Am I gonna invest or not? All right. So this is my set of decision variables. Objective function is I want to maximize the PV, net present value. Objective is net present value, which I'm going to maximize. And it's going to be, so if I invest in plant expansion, I'm going to get 90,000. So 90,000 times the decision variable regarding plant expansion, the binary decision variable regarding that, plus 40,000 times the binary decision variable for the warehouse expansion, and so on. Or I can use some product function. The present values multiplied by the investment decision one by one, and sum of them, all right? So that's my objective function. Next thing would be to write down the constraints. For each constraint, I'm gonna write down the left-hand side and the right-hand side. So let me just copy and paste the list of years requirements. So for each year, the amount that I need is gonna be the sum product of the amount, let's say for year 1, the amount that I need for different projects at year 1, the amount of capital that I need at year 1 for different projects, multiplied by the decision regarding those projects, whether or not 0 or 1, right? So that's gonna give me the total amount that I need at year 1, except that since I'm gonna copy paste my formula, I'm gonna fix these values by either F4 on Windows or Command T on Mac. Okay. So that is my left-hand side for year 1. And that has to be less than or equal to 40,000, which is the total capital available at year 1. All right. And now I can simply drag it down. And if I look at the last one, year 4, the total amount is 35,000, but the total amount used is the sum product of year 4 capital requirements multiplied by the decision regarding investment in different projects. So I have the constraints now, all the 4 constraints. I have the objective function, and I have the list of decision variables. So let's go ahead and solve it in Excel. So I'm gonna call the solver we want to maximize the objective function NPV by changing the 4 decision variables subject to, I'm gonna add all of them together. The left-hand side less than or equal to the right-hand side. Add. All right, change the solving method to simplex. There's one last thing. There's this notion of binary variable. I need to make sure that my decision variables are gonna come out at the end as binary variables. So I need to add that as a constraint. So I want my decision variables to be binary. All right. So objective function maximize by changing the decision variables, 4 of them, subject to the constraints, the capital requirement constraints in 4 years, and the binary constraints for the decision variables. I think I'm all set. If I press solve, as you can see, Excel found a solution, feasible, optimal solution. All constraints and optimal conditions are satisfied. And I have the answer report, which I'm not gonna look at it right now. I'm gonna look here. So the optimal set of projects are gonna be everything except the new product research, right? So I can expand plant, I can expand the warehouse, and I can buy new machinery. And if I do that, I'm gonna be within the available capital budget that I have. The only year that I'm gonna use up all the budget is gonna be year 3, is gonna be the one that is binding. In all other years, I will have some slack. And the total present value that I can get out of these projects is going to be $140,000.